How mathematics laid the foundation for artificial intelligence. 1. Introduction. The story of artificial intelligence, AI, is deeply intertwined with the history and development of mathematics. From the early days of philosophical inquiry into the nature of thought and reasoning to the cutting-edge machine learning algorithms of today, mathematics has been the bedrock upon which AI has been built. This essay explores the crucial role that various branches of mathematics have played in the birth and evolution of AI, highlighting how mathematical concepts, theories, and techniques have shaped our understanding and implementation of intelligent systems. 2. Early mathematical foundations. The roots of AI can be traced back to ancient times when philosophers and mathematicians first began to ponder the nature of thought and reasoning. Greek philosopher Aristotle's work on syllogistic logic in the 4th century BCE laid the groundwork for formal systems of reasoning. This early form of logic would later evolve into the mathematical logic that underpins much of modern AI. In the 17th century, mathematicians like Gottfried Wilhelm Leibniz dreamed of a universal language of reasoning, which he called the calculus ratiocinator. Leibniz envisioned a system where all human knowledge could be represented symbolically and manipulated according to logical rules. While his vision was far ahead of its time, it presaged many of the ideas that would later become central to AI. The 19th century saw significant advances in mathematical logic, with George Boole's development of Boolean algebra providing a mathematical basis for reasoning about truth values. This work would prove instrumental in the development of digital computers and subsequently AI systems. 3. Logic and computability. The early 20th century brought revolutionary developments in logic and computability that would form the theoretical foundation of AI. In 1931, Kurt Gödel's incompleteness theorems shook the mathematical world by demonstrating the limitations of formal systems. While these results posed challenges for AI, they also spurred further research into the nature of computation and reasoning. Alan Turing's seminal work on computability in the 1930s introduced the concept of the Turing machine, a theoretical model of computation that would become fundamental to computer science and AI. Turing's later work, including his famous 1950 paper, Computing, Machinery, and Intelligence, which proposed the Turing test, directly addressed the question of machine intelligence and laid out many of the key issues that would occupy AI researchers for decades to come. The development of formal logic systems, such as propositional logic and first-order predicate logic, provided powerful tools for representing knowledge and reasoning. These logical frameworks became the basis for early AI systems, including expert systems and logic programming languages like Prolog. 4. Statistical methods and probability theory. While logic provided a foundation for symbolic AI approaches, statistical methods and probability theory opened up new avenues for dealing with uncertainty and learning from data. The work of mathematicians like Thomas Bayes in the 18th century laid the groundwork for probabilistic reasoning, which has become increasingly important in modern AI systems. In the 20th century, the development of statistical learning theory by Vladimir Vapnik and others provided a rigorous mathematical framework for understanding machine learning. This work led to the development of support vector machines and other powerful learning algorithms. Bayesian networks, developed in the 1980s by Judea Pearl and others, combined probabilistic reasoning with graph theory to create powerful tools for modeling complex systems and making inferences under uncertainty. These techniques have found wide application in AI, from natural language processing to computer vision. 5. Linear algebra and optimization. Linear algebra has become a cornerstone of modern AI, particularly in the realm of machine learning. The representation of data as vectors and matrices, and the ability to perform efficient computations on these structures has been crucial to the development of many AI algorithms. Key concepts from linear algebra, such as eigenvalues and eigenvectors, principal component analysis, and singular value decomposition, have found numerous applications in AI. These techniques are used for dimensionality reduction, feature extraction, and data compression, all of which are essential in processing the vast amounts of data used to train modern AI systems. Optimization theory, closely related to linear algebra, has been equally important. Many AI problems can be framed as optimization problems, where the goal is to find the best solution from a set of possibilities. Techniques like gradient descent, which have their roots in 18th and 19th century mathematics, are now fundamental to training neural networks and other machine learning models. 6. Information theory. Claude Shannon's groundbreaking work on information theory in the mid-20th century provided a mathematical framework for understanding communication and information processing. While initially developed for telecommunications, information theory has had a profound impact on AI. Concepts like entropy and mutual information have become essential tools in machine learning, used for feature selection, decision tree learning, and measuring the performance of AI systems. The idea of minimizing description length, derived from information theory, has led to important principles in machine learning, such as Occam's razor and regularization techniques. 7. Neural networks and deep learning. The idea of artificial neural networks, inspired by the structure of biological brains, has its roots in the work of Warren McCulloch and Walter Pitts in the 1940s. However, it wasn't until the development of the backpropagation algorithm in the 1980s that neural networks began to show their true potential. The mathematics of neural networks draws heavily on linear algebra, calculus, and optimization theory. The backpropagation algorithm, which allows for efficient training of multi-layer networks, is essentially an application of the chain rule from calculus combined with gradient-based optimization. The rise of deep learning in the 2010s, enabled by advances in computing power and the availability of large data sets, has led to breakthroughs in areas such as computer vision, natural language processing, and reinforcement learning. The success of deep learning has also spurred new mathematical research, such as exploring the geometry of high-dimensional spaces and understanding the dynamics of optimization in deep networks. 8. Modern AI algorithms and techniques. Today's AI landscape is characterized by a diverse array of algorithms and techniques, all of which have deep mathematical foundations. Some notable examples include support vector machines. Based on statistical learning theory and optimization, SVMs find optimal hyperplanes for classification and regression tasks. Random forests. Combining ideas from statistics, information theory, and graph theory, random forests are ensemble learning methods that construct multiple decision trees. Generative adversarial networks, GANs. These leverage game theory and optimization to create a competitive process between two neural networks, enabling the generation of highly realistic synthetic data. Reinforcement learning. Drawing on Markov, decision processes, dynamic programming, and optimization theory. Reinforcement learning algorithms enable agents to learn optimal behaviors through interaction with an environment. Attention mechanisms and transformers. These architectures, which have revolutionized natural language processing, rely heavily on linear algebra and information theory to model complex dependencies in sequential data. 9. Challenges and future directions. As AI continues to advance, new mathematical challenges and opportunities are emerging. Some key areas of ongoing research include interpretability and explainability. Developing mathematical frameworks to understand and explain the decisions made by complex AI systems, particularly deep neural networks, is crucial for building trust and ensuring responsible AI deployment. Robustness and adversarial examples. Understanding the mathematical properties of AI systems that make them vulnerable to adversarial attacks and developing theories to create more robust models is an active area of research. Causal inference. Integrating causal reasoning into machine learning models to move beyond mere correlation and towards true understanding of cause and effect. Relationships is a major challenge that draws on probability theory and graph theory. Quantum machine learning. As quantum computing develops, new mathematical frameworks are needed to harness its potential for AI. combining quantum mechanics with machine learning theory. Continual learning, developing mathematical models for systems that can learn continuously over time, adapting to new information without forgetting previous knowledge, is crucial for creating more flexible and adaptable AI. Ethical AI. Formalizing ethical principles into mathematical frameworks that can be incorporated into AI systems is an emerging field that combines philosophy, logic, and decision theory. 10. Conclusion. The development of artificial intelligence has been and continues to be fundamentally a mathematical endeavor. From the logical foundations laid down by ancient philosophers to the complex statistical models powering today's deep learning systems, mathematics has provided the language and tools necessary to formalize, implement, and analyze intelligent behavior in machines. As we look to the future, it's clear that advances in AI will continue to be driven by mathematical innovations. The challenges facing AI, from improving performance and efficiency to ensuring ethical behavior and interpretability, all require deep mathematical insights. Moreover, the relationship between mathematics and AI is bidirectional. Just as mathematical advances enable new AI capabilities, the challenges posed by AI are spurring new mathematical research. This symbiotic relationship promises to push both fields forward in exciting and unpredictable ways. In conclusion, the story of how mathematics started AI is not just a historical account, but an ongoing narrative. As we continue to pursue the goal of creating truly intelligent machines, mathematics will undoubtedly remain at the heart of this endeavor, providing the rigorous foundation upon which the future of AI will be built. This essay has traced the mathematical roots of AI from early logical systems through to modern deep learning techniques, highlighting the crucial role that various branches of mathematics have played. It's clear that without these mathematical foundations, the field of AI as we know it today would not exist. As we look to the future, the continued interplay between mathematics and AI promises to yield new breakthroughs and push the boundaries of what's possible in artificial intelligence.